Good afternoon. What we'd like to do today is we'd like to pick up where we left off last class, doing a little bit on mixture proportioning. And anybody want to tell us a little bit about what we learned about aggregates and mixture proportioning from last class? Get us all back into the mood after we watched one of the most disappointing football seasons of all time. I thought it was disappointing, and I'm a Jets fan, so there was a whole lot of enthusiasm by watching the defeat, but
Go down as the greatest Super Bowl ever.
probably. But I wanted to see him hang 80 points on him. So.
That's true.
More importantly, back to concrete, which is allegedly what this class is about. What were we covering last week?
It's
Aggregates.
durability of aggregates.
So we said there was durability. There were a couple different issues that we were worried about, and the main issues for the durability of aggregates were
Freezing and thawing.
decracking, associated with freeze and thaw processes, and
Yes, sir.
alkali-silica reactivity, which is the alkali coming from the fly ash or the cement or the surroundings, reacting with amorphous silica in the aggregate, causing an expansive gel, which would lead to a fracture. There were some other properties of the aggregates that we were really interested in, and those properties were the internal porosity in the aggregate itself, because that's going to dictate the moisture conditions of the aggregate, and also the
Surface area.
surface area, which we are going to get at by determining the what's the weights. How do we determine surface area? What's the typical protocol for getting some information about surface area? Surface area is going to be related to the size of the aggregate. We get information on the size of the aggregate from what typical type of engineering test? Sieve analysis. So we'll do a sieve analysis to give us some information about how those particles pack together. We'll also get a little bit of information on how much surface area they have. Now we ended, right before we went over the holidays, or not even holidays, the weekend, we started to talk about the mixture proportioning procedure, and we started off with the manual of concrete practice, which is shown here on the slide. And we basically said that the ACI's manual of concrete practice will have one of these committees that will be dedicated to a logical, straightforward series of steps that will help us in mixture proportioning concrete. And the committee that's going to deal with mixture proportioning is 211. ACI 211 is the committee on mixture proportioning, and they have a fascinating read. And I think it's okay that I scanned this one page because you can't read it anyway. I got it, made sure I made it fuzzy, and that was on purpose so I wouldn't get yelled at by ACI. But you can see that it goes on and on and on for pages, telling you what the appropriate way to mixture proportion is. I personally find this to be a little bit boring. I can only get through about the first paragraph before I completely am comatose. So what I've tried to do is I've tried to assemble this into a great 10-step program. And we've talked a little bit about assembling local materials, getting information on the material properties, what type of concrete structure we're designing, what it's going to be exposed to. I mentioned that today during lecture we are going to see some of these lovely yellow slides. They are kind of like a pastel yellow color that tells us that spring is right around the edge, right around the corner, even though my main man from Punxsutawney said it wasn't. All right, isn't that the greatest job in the world? Be a big fat rodent who lives at the library, who comes out once a year and gets held up in the air by a bunch of people dressed in funny coats. All right, that's a whole different thing. All right, but what we're going to do is we're going to talk about using this lovely yellow pastel color. We're going to go through a design example so you can see how we would actually be performing each of these steps. Now, when we ended on Friday, we were talking about the fascinating topic of slump. Slump is a test that people perform on concrete, and a lot of people think that it's mainly there to assess workability. I will point out that it's really there to assess consistency and will tell us something about the workability of the concrete that we're after. So the slump test in all of its splendor is not really much more complicated than what I'm going to describe here. We're going to take a very expensive metal cone. We are going to put 3 layers of concrete into that metal cone using a very specific size rod that is specified by ASTM. We will smack the concrete 25 rods per layer. We'll do it a third of a layer at a time by volume until we fill the entire cone. Once the entire cone is, you will slowly pull the slump cone off of the fresh concrete straight up, and you will measure the amount that the concrete sinks. The amount that the concrete sinks or slumps is the number that you will hear people referring to as the slump number. So if you go out and someone tells you it's a slump of 4, at least in this region of the world, that slump of 4 means that it is 4 inches. Okay, so you can see at the top here is a concrete with a low slump. This looks like it's about 1.5 inches or 2 inches of slump. You can see at the bottom a high slump concrete where we've got about 9 or 10 inches of slump, where we're really getting out of the reasonable range of what that concrete should actually, or what that slump should actually be measuring for this particular test. Now, when you choose the slump early on in the process, it is going to be coming out of a table that looks something like this. It's table 6.2.2 from ACI. And basically what they're going to do is they're going to give you some information on where the concrete is going to be placed, whether it's a pavement, whether it's a mass concrete, residential construction, and then it gives you some approximations on what the slump should be for those applications. One of the things that I will point out here is there is a whole lot of art in choosing this number properly. I will provide you with this statement, even though I guarantee that someone will want to ask me a question about this later. There is no theory behind what slump you want. All right, you have to make an assumption based on where the concrete is going, what type of equipment is going to be used to place it, how stiff the concrete you want. It's simply an input right now in the design process. If I were redesigning the way concrete mixtures are done today, I would not have slumped this early on in the whole process. This table comes from the early 1900s, where there were not chemical admixtures that we could be using to alter the process very quickly. There was not the amount of control we had, so slump was one of the early things that people were using because they were placing the concrete typically by hand. Typically, if we're looking at our particular example, we're looking at a beam. Beam should be somewhere between a minimum of 4 inches and a maximum of 6 inches. So a 4-inch slump is what we're going to be typically looking at for this application. And you can see that we are off and running, and we've used this table in all of its glory to tell us the answer to step 2. Sure.
Is the residential construction concrete on steroids or something that it needs an asterisk or?
Oh, residential, yeah, well, it is on steroids, and it'll be in front of the Congress. We'll be looking at it next. But the reason that we're going to look at residential concrete with a little asterisk is because there's a new committee that's looking specifically at residential concrete. And I'll mention something very specific. Residential concrete, you should assume, unless you've heard anything else, and I apologize for the colors on this slide. As I mentioned before, I'm trying to create all the colors so that they match up nicely, and I obviously missed this one in my hurry to convert them all to a dark background. I know it may sound odd, but I usually do this while watching TV and petting the dog at the end of the day, so occasionally I miss a slide on my way through. But rules of thumb on ready-mix concrete, if it's going to a residential application, you typically want to design for about 6 inches. The concrete will make it 6 inches. The contractor will make it 6 inches typically, unless you provide it. They will still likely try to increase the slump because they want it to flow very easily. I will put this in here because, as I mentioned a little bit earlier, I've had experience on both sides of the fence. I've been the person trying to enforce the slump on a construction site. I've also been the person who is running a crew with several big burly people who are placing the concrete, and I will tell you that much like everyone else, I gave the universal sign for rodeo, and if those of you who've never seen it before, it looks something like this. And basically the universal rodeo sign is telling us let's add water to the back of the truck, and there'll be a nice tip in it for you driver at the end of the day. The reason that contractors are going to do that is because they want the workers to be happy. What is not understood many times is the universal rodeo sign comes with a decrease in strength and a decrease in permeability, a decrease in durability. So what we want to try to do at this stage is we want to try to make the potential for the contractor to want to add water very, very low, and we want to design from a high slump right from the start. We want to design something that people can place without having to add water, so there isn't a huge fight when it gets out on the construction site. General rule of thumb, An inch of slump is about 10 pounds per cubic yard of water. All right, so generally when they start adding water in the back of the truck, you don't want them doing this on site, because them adding this is basically watching how much water is coming out of a hose. They have no idea how much water is really being added into the back of the truck, and you're altering all the mixture proportions at that point. And the other thing I will say, so that I do not advocate using the rodeo sign when the truck shows up on site. Before someone leaves here and writes down, Professor Weiss said use the rodeo sign whenever a truck shows up. You are not to add water on site.
On residential construction, don't the concretes there experience less strain? And you're just like, usually it's wood construction over it and not as much loading anyway?
Well, it depends what it's designed for. But, I mean, this is where we come back to, if it's designed to be 4,000 PSI concrete, then you should know that you've got 4,000 PSI concrete. Okay. If it's 1,500 PSI concrete, then it's 1,500 PSI concrete. In residential construction, strength is generally not the main limitation. It's usually going to be a durability problem that pops itself up, or a shrinkage problem. And the real issue that I will point out, a lot of what we deal with is variability from one point in construction to the other point. So it's really, you'll have 10 trucks that are, this may be on a more commercial project, 10 trucks that are perfectly designed, one that has way too much shrinkage, and that's where you're going to get your cracks, or that's where you're going to get your scaling, and that's really what people are concerned about.
What about, like, if there's a maximum water to cement ratio, and would it be acceptable to add water on site then? Like, say you do initial testing and you come out below it?
There are some criteria on when you can officially add water on site, and I will cover those later on. Okay. All right, you can do it, provided there are like 6 caveats that you can't exceed the maximum water cement ratio, and there are actually people who design the concrete and hold water back so that they can do that on the site, so that the contractors are happy. I don't think that's the best way to design concretes, because you have much better controls at the plant, and everything's on the batch tickets. There's less confusion. So I think there are ways to design it properly, and I will get to that when we talk about quality control and field concreting issues, I promise. But in general, unless you're very aware of all those criteria, don't add water. All right, the general rule. Now, there are a few exceptions, but a lot of time people just want to add it for no apparent reason other than it makes it easier to work. All right, the big thing I want to get at this point here is, make sure that you design the slump so that some human person can place it. Right? If you're designing a 1/2 inch slump, and there are concretes that are designed with a 1/2 inch slump, recognize what it's going to take to put that into the forms. Right? Now, typically something designed with a 0 inch slump or a 1/2 inch slump isn't going to be moved by human hands. It's going to be conveyed. It's going to be put through a screw auger. It's going to be consolidated using a commercial paver, which we'll show in a couple of seconds. There's a lot more energy. There's a lot more equipment there to do the work of consolidating the concrete. So slump, and I will say at this point, slump is relatively arbitrary in the process when you select it. There's a table there to provide some guidance, but it's a relatively arbitrary step in the whole process. Step 3, estimate the maximum size of the aggregate. As we mentioned before, some of these slides will look familiar because we've discussed them before. The maximum size of the aggregate, we're typically going to be looking here at our coarse aggregate. We have our 2 criteria. We have the depth of the slabs on grade, so it could be D/3. We have the other criteria where it either has to fit between the rebar, 3/4 of the spacing has to be greater than the maximum size of the aggregate, or it has to be 1/5 of the distance between the formwork. Remember that the size of the aggregate that you are selecting will have a dramatic impact throughout the rest of the process, and it has a dramatic impact on the rest of the process because it is going to dictate the volume of paste. So what you are really doing in this step is you are really making a determination of how much paste you want to have in the overall system. So you may say, well, I'm just picking the aggregate. It's not a real big deal. It's not going to have any impact on anything else. Oh, but it will. It will influence the amount of paste that comes up in the system. Typically, the rule of thumb is you want to try to use as large a size aggregate as is reasonably possible. Typical sizes, you'll see people using inch, 1.25 inches, 1.5 aggregate as their maximum size aggregate. And then we've got our size distributions that I'm not going to go through great detail here, but the size distributions will also have a little bit of an impact on the amount of water. As mentioned, the aggregate size will have an impact on the mixture proportions. It will also have an influence on some of the other properties. Durability can be influenced. We mentioned before, the smaller the aggregates, the less likely they are to experience decracking, typically because we fracture the aggregates where they would be likely to absorb a lot of water that causes the decracking problem. Also, smaller aggregates tend to be a little bit more resistant to ASR problems. Larger aggregates we're typically going to want for economy. They're typically going to be cheaper to produce. They also will allow us to get more paste into the system. Also, we can reduce shrinkage with larger size aggregates. Now later on at the end of the semester, I'm going to contradict this and tell you that the size of the aggregate makes no difference on the shrinkage. And I am going to try to cut this problem off at the beginning of class, and I'm going to tell you why there is a discrepancy in our notes. The larger aggregate is going to reduce shrinkage because it will lead to less paste in the system. All right, so all other things being equal, the size of the rocks makes no difference on shrinkage. However, larger aggregates allow us to use less paste. Using less paste will reduce things like paste-related problems and will reduce things like shrinkage. Somewhat clear? I'm sure it'll be confusing by the time we get to the end of the semester. All right, so typically in the types of problems that you will get for homework, since you're not necessarily familiar with the local markets of whatever the problem is that you're designing the concrete for, we will tell you what the size of the aggregate is. So step 3 goes fairly quickly. Here again, you're using the maximum size of the aggregate based on the distance in the forms and the distance between the reinforcing steel. Now, I will mention that the 2 most difficult steps in the entire process are steps 4 and 5. Steps 4 and 5 are the ones that require talent in the mixture proportioning process. They are the only 2 steps that are even somewhat intriguing. The rest of them are either fairly arbitrary, in my opinion, or are direct calculations so that every engineer is going to be happy. Now, what's interesting is when we teach this at the undergrad level, the only 2 steps that they don't like are steps 4 and 5 because there's actually engineering judgment that goes into them. And what we're going to try to do for probably the rest of the lecture today is to look a little bit about some of this engineering judgment that goes into steps 4 and 5, give us a little bit of insight on all the complexities that are associated here. So the first step is to assemble information. That's pretty straightforward. The second step is to make an assumption about the workability. This will be how the concrete can be placed, where the concrete is going. The third step is the maximum size of the aggregate. And again, remember that the size of the aggregate is going to determine the volume of the paste. So inherent in step 3, we're saying something about the volume of the paste. That's typically when we want to use the largest size aggregate possible. Now what we want to do is we want to jump ahead and we want to talk a little bit about water and air for the system. As we mentioned before, all right, in general, drinkable water is usable water. The amount of water is going to be influenced by the aggregate size, shape, and gradation. Why is it influenced by the aggregate size and shape and gradation? Water is going to comprise paste. So the more paste you need, the more water you're going to need. So this is sort of a way of getting at, well, this is going to be a fraction of the paste, so it's going to be influenced by the aggregate size. It's also going to be influenced by the chemical admixtures. Most notably, the amount of water that you need is going to be influenced by the use of a water-reducing admixture. Right? It shouldn't come as a shock to most of you that water would be influenced by a water-reducing admixture. And also placement needs will tell us a little bit about the water. The more fluid the concrete needs to be on site, the more water you're going to need to add to the system. Now what I've done here is I've tried to move a little bit of a step past what is in ACI 211. And I've taken the data that you will see in the tables in 211 and I've made it much more exciting by making it a picture or a graph. So if you say, well, I've gone to ACI 211 and I don't see this, I don't know where he came up with this, This is the data that's given in the ACI tables. The only thing that I've done here is I have fit a few curves to the data that's in those tables, and I have said that we can start to make a relationship between the water content, or the estimated water content, which is on the y-axis, and the desired slump, which is on the x-axis. You will notice that there are a series of curves. These curves all have a number on top of them. That number that's on top of them is the maximum size of the aggregate. So when you go into ACI 211, you will see a table. That table contains the exact same information that's here. The basic concept is that there's going to be some relationship between the water content, the slump, and the aggregate size. And that correlation, or that relationship, is demonstrated in this picture. I will also point out that this graph is wonderful because it allows people who love the metric system and people who love the conventional U.S. system to coexist. It is a wonderful table from that standpoint. So we have pounds per cubic yard, we have kilograms per meter cubed, we have inches, we have millimeters, all on the exact same plot. Now, as mentioned before, the size of the aggregate influences its surface area. So I've done this simply with spheres. I've shown you that if we had a whole bunch of spheres, they were single-sized spheres, and we put a whole bunch of them together, all right, to fill up a cubic foot, what you would notice is the surface area of the spheres increases as the aggregate size decreases. Right? You could actually figure out the relationship here. Does anybody know how we would get toward the relationship?
Volume to surface.
The volume to surface relationship, right? So you could probably figure out how much surface area there is on a sphere or a circle. Most of you have taken enough math to figure out the surface area of a circle or a sphere. You could also look at the volume of that sphere, and you will realize that there is a relationship between them. Okay? You could take the derivatives, and you could find that this has a very specific function to it. Right? What I will point out here is this is the same type of concept, but applied to real aggregates. So if we make some assumption on those aggregates, we would see that for typical ASTM C33 gradings, all right, C33 requirements, we could have aggregates that are on the coarse side of those gradings or on the fine side of those gradings. And what's plotted here is the aggregate size on the x-axis versus the surface area per cubic foot of aggregate on the y-axis. And you can see that as long as we're within the specification, we're going to be somewhere between these two lines. The coarse aggregate is going to tend to be on the bottom of the bottom line. The finer aggregate, more fine particles, is going to be on the upper part of this line. Now, this will also start to give you a little bit of an insight that when we pick out our aggregate, the gradation is going to have a little bit of an impact. Because you could have an 1.5-inch aggregate that acts like a standard 1.5-inch aggregate, or you could have one that's acting like a coarser grade or a finer grade. And the way that we're going to see that is how much paste or how much surface area those aggregates are going to have. So we're going to see a slight adjustment depending upon how much surface area or how finely or coarsely graded they are. So some of the basic trends that you will notice on this graph, again, it's the wonderful graph that relates the metric and the U.S. systems together. It is a fantastic graph because it gives us some of the basic fundamental information that we would expect. As we would move from big aggregates, and I will draw a big down here, smaller aggregates on top. As we go from big aggregates to small aggregates, we would expect the water demand to increase. We have more surface area. Well, let's check that out on our graph. As we go from big aggregates, 2-inch 50-millimeter aggregates, to 3/8-inch aggregates, the water demand has gone up. It's increased. So far, it doesn't sound like I'm telling you a lie. Smaller aggregates, more surface area, we're going to require more water in the overall system. The next basic trend that we can start to trace out is looking at the x-axis. We know that if we want concrete that goes from a stiff concrete to a concrete that flows like the river, we are going to move from the left to the right-hand side of this graph. As we move from the left-hand side of this graph to the right-hand side, we will see the slump will be increasing. To increase the slump, we will add water. So you will see as we move from the left to the right, and we're looking at the same aggregate size. In this case, let's pick 1.5 inch aggregate. As we move from the left to the right, we go up. As we go up on this graph, we are increasing the water demand. So far, this graph seems to be telling us the truth. Smaller aggregates have a higher water demand. More slump has a higher water demand. That's all we're trying to capture with this particular graph. Okay? So for our example, if we took a 4-inch or 100 millimeter slump, we could enter the graph with that 1-inch or 4-inch or 100 millimeter slump where it intersects our maximum size aggregate here at 1.5 inches. We would simply now read off the estimated water content. So we would read this off as being something like 290, 295 pounds per cubic yard. Step 4 is almost under the belt. All right, so as I mentioned, we read this off. We've drawn this so it's much more accurate than my crazy mouse drawing here. It's about 290 pounds per cubic yard. If you don't like that graph, you can go back to ACI 6.3.3 from ACI 211. All right, this is the table. It tells us 1.5 inch aggregate. It tells us somewhere around a 4-inch slump. Instead of 290, it gives us something around 300. This is simply because we are curve fitting and we're getting some approximations on those numbers. Okay. If you wanted the metric version, here it is in metric. You will get very, very similar numbers to what we saw in the previous graph. Now, one of the things that I would like to point out is there's an additional table. There's an additional line on this table that doesn't relate to slump. All right, and it's listed along here at the bottom. And this tells us the approximate amount of entrapped air in non-air entrained concrete given in percent. Well, what does that mean? That means when we start to whip this thing up, we put all the materials in the back of the truck, we are going to start the process of mixing. Right? We are going to start mixing the entire system together. And as we mix the entire system together, we are going to generate air in the system. All right? We are going to start to generate bubbles. We are going to start to generate air like your finer cappuccinos. Right? You go to a cappuccino, the solution to take a nice fluid milk and make it a frothy treat that you can charge $12 for a cup of it. All right? You are going to mix it. You are going to blow hot steam into it. You are going to create air bubbles in the system. As we mix the concrete together, we will get air mixed into the system that we don't lose. The amount of air that gets mixed into the system is estimated here in the bottom. And what I will point out is for a larger aggregate, you would expect to have less air. For smaller aggregates, you would expect a lot more violent mixing and get a lot more air in the system. And this is simply a percent of the entire volume. So for our 1.5 inch aggregate, 4-inch slump, we would expect to get about 1% of air whipped into the system during the mixing process. This would be entrapped air or air that is trapped into the system by the mixing process. Okay? And it's just a simple rule of thumb that's on the bottom of this graph. Same information given when we look at the graph in metric units. Okay. Questions on this up to this point? Now there is one small caveat, and it says the amount of entrapped air in non-air entrained concrete. So it must mean that there is a different type of concrete that exists, and to get to the high-class concrete, we will rely on our good friend Homer Simpson here. All right, Homer Simpson has had the same problem that I've had, I am sure, on occasion, that you have left for work Friday morning running late and you have forgotten to put your favorite tasty beverage on ice so that it is ready for you when you come home after a hard day's work on Friday afternoon. If you take this beverage and you throw it into the freezer and you forget about it and fall asleep on the couch, you will awaken to what?
A can of beer.
Well, you may awake to a burst can of beer. I will usually wake to my wife's voice sounding like a nightingale, reminding me of the freezing process of beverages in a freezer. All right, so we will go through this in a little bit of a picture form here. We've got water inside of a closed vessel. As that water begins to freeze, we are going to create a solid. The solid form is going to be larger than the fluid form. So we are going to start having the jar restricting the expansion. We're going to start building up a pressure, and when it gets high enough, we will actually fracture the entire system. So this is where the soda can, beer can, bottle will burst inside of the freezer. Concrete is a lot like the Duff beer can inside of the freezer. All right, this is a picture of concrete. This is from the PCA concrete exposure site up in Skokie, which is right outside of Chicago. All right, for those of you who've driven past Chicago, you get to the Old Orchard Mall, one of the real large malls up there. The Portland Cement Association has a lovely garden outside that looks at concrete like this. All right, this concrete was left exposed. It was non-air entrained concrete. When the water inside of the system begins to freeze, it creates a pressure that will cause a fracture inside of the system, will cause the concrete to disintegrate and start to fall apart. For those of you who say, I couldn't imagine concrete falling apart, I've never seen it in my life, if you would like a very good example of this, walk across the street, and in between PEFQ and McDonald's, there is a sidewalk. That sidewalk is probably one of the best examples of non-air entrained concrete falling apart during freezing and thawing. Right? Huge chunks of that fall apart every single year. It's fantastic. It is a great learning tool. I hope they never fix it. All right, because it is great. All right, a couple things that you need to remember for freezing and thawing. Air entrainment is incredibly important, and we will talk about that. And I don't want to minimize air entrainment, but there are a few things that have to come together for freeze-thaw to be a problem. It's kind of like one of these issues of the perfect storm has to be brewing. You can't have freezing and thawing damage in the Keys of Florida because it doesn't freeze. So it has to get to a cold temperature. Right? One of the other issues that you have to have, and this makes sense when you think about it, unfortunately most people don't stop to think, that you have to have water in the concrete. You have to have a lot of water in the concrete. And this is a typical graph that shows this concept, I think, very clearly. This is from the 1950s. And you will hear people who basically claim to have never ever experienced or seen or heard of this type of concept before. What's plotted along the x-axis is the degree of saturation. So you can think of this as the amount of water, or the percentage of water per the total amount of water that concrete could suck up after a long period of time. All right? So 100% means the concrete is saturated. It's not going to absorb any more water. 50%, it's got 50% of the water that it would have at a complete saturation, and this is just a graded scale. On the y-axis, we have its resistance to freeze-thaw damage or resistance to frost. You will see this marked a few times. You'll also see people talk about this as the stiffness degradation. A number like 100 means that it hasn't degraded at all. The stiffness after freezing and thawing is exactly the same as the stiffness or elastic modulus before the freezing and thawing took place. A number like 0 means that it's crumbling in your hands. All right, so it means that it's completely degraded the stiffness of the overall material. Now, what you will see is we've traced out something that looks like the flag of probably some small country. Right? Someone will be stealing this as a flag for their country and denoting their freeze-thaw resistance and their independence from the rest of the world. You will see this green, lime green area, and the lime green area is concrete that has a relatively good durability. You can see all of these numbers are up around the 100% range. It's also not uncommon to find stiffnesses that are even higher than what they were initially because of continued hydration. But you have a region where the concrete is behaving fairly well. It's good concrete. We have a region where everything that's out there is failing, and it is poor, poor, poor concrete. It's falling apart. It's just being degraded. And then we have this region that's kind of a no man's land. Right? Some of it's okay, some of it's not so okay. But generally, it's just a transition region between these two regions. One of the things that's very interesting, and we can sit and we can fight about where this point should be, but generally, between somewhere around 86 and 91, 92% is where this no man's region falls. Everything that's above this region has too much water in the system, and the system just falls apart. It is saturated, and the system falls apart. Anything that stays below this region stays relatively dry. And even though it's undergoing freezing and thawing, the concrete is not going to fall apart because there is space inside of the system for the pressure to be relieved. Now, one of the things that's very interesting, and some of you may know this, but the amount of volume difference between ice and water is 9%. So what you will notice is that if you came in here at 91%, that's right around the middle of the no man's region. Right? 9% volume change when water goes from water, fluid state, to ice. It expands about 9%. There's also a belief that there's a little bit of range here because it accounts for the pore solution and it accounts for some of the other effects that could be taking place inside the system. So if we allow the system not to saturate, we can make a concrete that is very, very freeze-thaw resistant. So two of the things that you need to have concrete fall apart due to freezing and thawing, it has to freeze and it also has to thaw. And I think I mentioned last class that if you have one freezing event each year, it may not be as dramatic as something like Indiana or Ohio or Pennsylvania, where it's freezing and thawing 2 or 3 times a day. Right? And it also needs to be saturated, needs to be full of water. This is why you can see places where the concrete will just be falling apart, where 2, 4, 6 feet away, it's the exact same concrete, but it's behaving pretty well. It has to do with the degree of saturation inside of the concrete. So the basic idea here is shown conceptually. We've got our temperature. Concrete's right around 0 degrees. As it freezes, that water is going to expand. It's going to create a pressure. When it expands, it is going to crack the overall paste. So the solution was to build a 2-story cow. No. All right, this is one of my favorite cows. Not only did someone go through the effort to build a 2-story cow, but in order to conveniently get inside the cow, they built a large platform and stairs to climb in through the hindquarters of the cow, which I always find is somewhat interesting. One of the things that we'll talk about here is a solution to the freeze-thaw problem that was kind of discovered by accident in the 1930s, although it had been discovered by the Romans when they were developing their concretes. And we'll talk about this in a little bit more detail. There's some evidence to show that there were concrete pavement sections in New York that were behaving well. There were concrete pavement sections that were falling apart very quickly as soon as they were being placed. And there was an investigation to find out what was causing these concretes to fall apart so quickly. There was a belief at the time that the concrete that was falling apart so quickly was being produced in sort of a shoddy method where people were adding things to help to make the concrete grind a little bit faster. We didn't talk about it a lot during the cement manufacturing process, but right before we go to the process of dumping the clinker into the ball grinder, and we start to drop the steel balls onto the clinker to grind it up into particles, there will also be some other stuff that's thrown in there to sort of accelerate the grinding process, and they're referred to as grinding aids. At the time that this was being done, there were some of the producers were using things like beef fat, fish oil, throwing those in because they will help the grinding process. They were also having different plants that had leaks. So things like some of the hydraulic fluid or some of the grease from some of the bearings was leaking into the overall system. And there was a big belief that if they could get rid of these grinding aids, this would be the solution to the problem. Well, a funny thing happened on the way to trying to prove that that was the problem. Turned out that those concretes typically exhibited better behavior than the other ones. And the basic idea here is that the beef fat, the fish oil, the grinding aids that were being used were going to help to create little tiny bubbles that we'll refer to as air entrainment from here on out that really allowed sort of a pressure relief when we started to generate pressures inside of concrete due to freezing. Okay. Now, I mentioned that the Romans knew this. Anybody know what the Romans added to their concretes?
Blood.
Well, the Romans had a lot of blood left over. They also had a lot of fat left over. They would mix those in, and their concretes would be freezing resistant. So much like the beef fat, apparently the fat of something that didn't behave well in comparison to a lion also has very similar long-term behavior. So again, to go back to the PCA exposure site, we've got the non-air entrained concrete that fell apart here on the bottom, the air entrained concrete on the top, and the basic idea here is the air entrainer, and this will be something that you will hear a lot of people talking about, especially on site. You will hear people talking about adding air to the back of the concrete truck. We do not specifically add air to the back of the concrete truck. There's not like a big truckload of air shows up and we pump it into the back of the truck. We add an air entraining admixture to the back of the truck. We add it into the mixing process. And the idea here is not necessarily to add the air itself, but what we're doing is we're adding something like something you may have played with a nephew or son, daughter, whatever. You see here somebody blowing bubbles. It is something that helps to stabilize those bubbles. So we are adding an air entrainer to the back of the truck of the concrete to capture the air that's generated during the mixing process. So we mentioned before that when we mix up the concrete, we are going to create air inside of the concrete. Many times this air will actually break down during the mixing action. If we just keep mixing it and mixing it, we'll create some air, some of it will break down. What we're actually doing is we're adding an air entraining agent that will have a chemistry that will help to stabilize the air bubble. By stabilizing that air bubble, it's going to create more air inside of the paste. And one of the things that's going to be much better about this than the other pores that we have inside of the system, these pores are going to be filled with air. Nothing. All right? So if we go back to our idea of saturation that we were talking about before, this is empty space inside of our concrete. This makes it harder for that concrete to saturate. So we now have a lot of little tiny air pockets inside of the concrete. And you can see an air entrained concrete compared to a non-air entrained concrete, we'll have something that behaves much, much better. The idea is when the water inside of the capillaries freezes, it will generate a pressure. That pressure can be relieved by the air bubble, and it may allow water or air pressure to go in and out of the bubble. Mike?
Are these air bubbles like connected to the pore structure, or are they like sealed off usually, so that it takes some micro cracking to get to the air bubble first, and then it will release the pressure immediately? Well, because I could see some degradation coming from that if that was the case, like if the bubble was completely sealed versus if it was connected to the pore structure.
But when you say completely sealed, you remember that our paste isn't a solid. It's a porous material. So the whole thing is being percolated by our capillary and gel pores. So the idea that there's a solid that's completely sealing it off is a little bit different. What you really have is you have, I don't know, like one of the finer micro Swiss cheeses with a big hole drilled in the middle of it. So you've got a porous system with some bigger holes in them. So the pores are all relatively connected. Now there is some discussion of, we may have to create larger fissures, we may have to create ways for water to move around. But one of the other things that we'll come back to is these pores are really well distributed throughout the system, so they're all over the place. All right, they're kind of like Starbucks. They're everywhere. You could, hopscotch across. Yeah, so they're really close, and there's not a whole lot of distance that needs to be traveled.
Okay.
Right?
These pores generally bigger than the capillary pores?
They tend to be smaller, but we'll come back to this and we'll discuss this a little bit more. They'll be around the same size range, and one of the big tricks to making a really, really effective air entrainer is to dictate the size. Most of the time, because we only want a certain volume of the entrained air inside of the system. So if you control the size, in effect what you're doing is you're making it more well distributed throughout the system. So you'll hear some people talking about things like micro air and their specific commercial products, which create a very fine porous system across the entire structure, and that's really sort of the holy grail of the air entrainment. Right, the basic way that these air entrainers are made, they are a chemical that will be inside the system. They're a chain, and one of the ends of the chain will be hydrophilic, one will be hydrophobic. For those of you who may not remember what that means, hydrophobic is it's afraid of water, it's scared of water, it's much like my dog. Hydrophilic is much like my dog in a swimming pool. He hates the bath, that's the hydrophobic side of him, but he loves to be swimming in a swimming pool or a lake or a pond or a big puddle or whatever else is out there. Okay, one end hates water, the hydrophobic end is afraid of water, the hydrophilic end really likes water. So this is the way that they're going to stabilize the air bubbles. They are going to preferentially align themselves so that one end or one tail of the chain is going to be inside of the air bubble. That's the hydrophobic end. The other one will be in the pore solution. These tended to be, for a long time, byproducts of other industries. Animal byproducts, here we see the fats that we were talking about earlier, byproducts of the petroleum industry, and also byproducts of the pulp and paper industry. This has changed a little bit over the last few years because some of these other byproducts are finding their ways into some other fine materials, and with Valentine's Day coming up, they're finding their way into things like lipsticks and chapsticks and things like that. So all of a sudden, if you're looking to try to make more money on your waste pulp and paper products, concrete may not be the place to do it. You may make more money by dumping it into lipstick or something of the like. So this is changing a little bit. Typical dose rates are very, very low. They're frequently pre-diluted for batching. One of the issues that we'll talk about when we start to do batching is we're looking at batching huge volumes at a time, and especially for chemicals that may be very, very powerful, they'll be diluted with water. Neutralized Vinyl resin is a very common one. As we mentioned before, these can be sensitive, especially to carbon, which is coming from the fly ash. So it's something that we want to be looking at. And also, any foam isn't necessarily good foam. So what we need to do is we need to make sure that the foam is very stable. So sometimes you'll hear people talking about a foaming agent being added into the mixture, and this is really to sort of try to, or defoaming agent, to try to control the overall system. So these air-filled spaces, these entrained air spaces, are going to be air-filled. The basic idea is they are going to sort of act as shock absorbers or places where the pressure can be relieved. So as the temperature drops, the idea is the pressure can be relieved or the water will go in there. It won't crack the overall paste. As the temperature goes back up, the system will return back to normal. Here we can see another flag. Again, this may be the country next to the country we talked about previously, the same colors. We've got poor durability, low air contents. Down in these air contents, you don't have enough air in the system to protect the paste. Typically, you're dealing mostly here with just entrapped air, big air, not well connected, hard for the water to be relieved. Transitional zone, 2 to 3%. Higher than 3 or 4%, we typically see good durability. You will see a lot of times on commercial jobs specifications of 6 or 7% air inside of the system. One of the things that I will point out as it relates to, one of the other things I will mention, we will come back and we will talk about air entrainers. More specifically, it'll be likely about 3 lectures from now. So we will come back and talk a little bit more about air entrainers. I'm specifically talking about them today in the context of giving some introduction and then talking a little bit about how they alter the mixture proportioning process. The basic idea here is the air bubbles, since they will tend to create these little air pockets inside of the system, they will act as a lubricant that reduces the friction between the cement particles and other cement particles, or because of aggregates. So they will have a system that flows a little bit easier. Because it flows a little bit easier, you can expect the amount of water that's needed in the system to be reduced. They're going to reduce a little bit of the paste because they're filling that part of the system up with air. So you can expect things to flow a little bit easier. You'll see a reduction in the water demand that I'll talk about in another second or two. Now there's one graph that I will point out that is incredibly controversial, so I will leave this as a tease for the end of the day. I will come back to this in a second. You will see, as we go into the next lecture, we'll see a table that now all of a sudden starts to talk about actually air entrainment. But as sort of the tease as we end off today, what I'd like to do is I'd like to present this, which comes out of another table in ACI that talks about how much air you need, and it depends on the exposure condition, whether it's mild exposure, moderate exposure, or severe exposure, and then it plots the air as a function of aggregate size. And that may seem really odd to start with. How would the freezing and thawing and the paste be dictated by the size of the aggregate? I can understand freezing severity, but not by the size of the aggregate. That's where we'll pick up next time, trying to answer that question.
Spaces of entrained air, and then you have the, like, I'm guessing that's your water, and you have air in the other ones, or is it the other way around where you have air and you're now air entrained? And
yeah, it's a little bit tricky. You will have air in the